Just a quick review of some atomic structure as the build up to the quantum mechanical model. Back in the beginning, Dalton, of course, had the solid sphere model with his, points of his atomic theory, identical, indestructible, can't be broken down, law of conservation of mass, that the atoms of different elements would combine in whole number ratios, that law of multiple proportions, all that good stuff, okay? Just a quick review, and I will let you know when we get on to the table here. This is more like Unit 2, but it is a progression, one building upon another, their evidence then used in the next set of ideas and so forth. Then, of course, we had Thomson, the cathode ray guy, the one that did particles through the cathode ray and realized that they were negatively charged because they attracted to the positive side of the electric field, that plate. And he discovered the electron and he came up with his plum pudding model. Now, of course, not holding true, but the positive medium, which was like the pudding or the, major part of the atom with the electrons being dispersed throughout, like the plums would be inside the pudding. Now Rutherford, the gold foil experiment, and Bohr was actually one of Rutherford's students, so that's really good to know. Rutherford had discovered the nucleus, positive dense center, and he shot alpha particles at gold foil. Most of them went through, which indicated that the atom had mostly empty space. However, a few of them bounced and deflected in different directions, that alpha particles being positive, positives repel other positives, so that's how the idea of the distinct positive center came into being. And he gave us the nuclear model. Nucleus in the center, electrons around it. Although he couldn't really explain where those electrons are or where they're going, so we're going to get into that part of the quantum mechanical model. Millikan, what you need to know about him, did this nice oil drop experiment. You can watch a video on it, but it's very complicated with electric fields and stuff. And you can see how he was able to calculate the mass of the electron. So, bringing you up to date, Rutherford, like I said before, they had started observing the fact that certain elements gave off certain colors in the flame tests. So they were able to start thinking about what was causing that, and the chemical and behavior of the electrons, the arrangement of the electrons in the atom. That was something that was starting to come into being as an idea. So we know that Bohr did the line emission spectrum experiments where he was able to see that certain elements, hydrogen specifically was the main one he studied, when given some energy, gave off certain bands of color. This pertains to your lab that's going to be due next class, so make sure that you go back over that. Make sure that you're explaining carefully how the electrons are moving out from the nucleus by absorbing energy, and the further they go from the nucleus, the more energy they're gaining, so the higher energy colors they will be emitting when they fall back to the ground state. Okay? So Bohr here, used this kind of experiment, so if you want to write that down in the experiment part of your chart, you can. And now we start filling in the blanks. So he added the location of the electrons by observing his hydrogen emission spectrum. Atoms still have a central nucleus according to the Bohr model, and they are present around the nucleus, moving in specific orbits. Each orbit has a specific energy level, of course, and the orbit is a specific distance from the nucleus. So those ideas there were created by Bohr, and the idea of a principal energy level still holds true. There are principal energy levels for the electron cloud and where the electrons will be. It's just that in those principal energy levels is a lot more complicated than just specified orbits. Okay? So that moves us on to Planck again, and remember Planck did experiments with light. He was looking at the quantized energy that was being absorbed and emitted by the light, and those discrete quantities amounts that were being absorbed and emitted. He labeled the smallest quantity of energy to be a quantum. Now, if they're absorbing or releasing multiple, then it would be a quanta. And it was, the release was in the form of the electromagnetic radiation that we would see if it was in the visible light spectrum. You could see the bounding patterns of the colors. Now, if it's out of the visible light spectrum, then you might have UV, you might have infrared, you might have gamma, you might have other forms of radiation. Just wouldn't be able to detect it with our vision. Okay? So, de Broglie, he's the one that took these ideas of Planck, and he also built upon his idea from Einstein too. In the previous one, we talked about Einstein, the photoelectric effect, and Einstein building on Planck's ideas where that he was thinking that light had the duality of wave-like and particle-like properties. Now, de Broglie built upon Einstein and Planck's ideas, came up with the fact that electrons have the duality as well. They can behave like waves and they can behave like particles. And so, the electron is allowed only certain possible wavelengths. Okay, that's that quantized energy. It's not going to produce every single wavelength. It's not going to be a continuous spectrum. They're going to have their certain banding patterns. And he predicted that all moving particles have wave-like characteristics. So you and I, when we are walking or moving, we're actually even giving off a very small wavelength as well. So anything that has, mass is going to give off a wavelength. Another thing that he showed was that there are possible circular orbits of electron are limited to whole numbers of complete wavelengths. So encircling around, say, a nucleus here, they would be in perfect whole number wavelengths. So like 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength. This one would have 4 wavelengths being able to go around in its orbit. Now, it's not exactly what's going on, but it was a good idea. And of course, the non-whole number ones did not work for this particular idea. The idea that there are whole number of complete waves and that the electrons behave as waves and has the duality of the particle and wave was de Broglie. So other bits of evidence, you saw this in the video as well, when they were doing the slits and firing the light particles at the through the slits at the wall, and we saw the discrete lines coming up. While comparing the visible light to the diffraction pattern to the electron pattern, they're very similar. So this is the other further evidence giving the idea that electrons have that particle-wave duality. Now Heisenberg. Here comes along Heisenberg. And Heisenberg did some research and ideas about the locating and finding the electron as well. But it is fundamentally impossible to know the position and speed of a particle at the same time. And those electrons in the orbitals, you can detect them, but then they move, so they're no longer in that other position that they were once in. So, of course, you can track and figure out where the electrons are, but if you use a device, say like a gamma ray, or you shoot any other electromagnetic radiation at it, then that particular particle will move, won't be in that position anymore. So it's pretty much virtually hard to know exactly. So this goes into the idea of probability of where the electrons are. They can track and look at the density of where they might be and where they're showing up, but we won't know exactly. And Schrödinger developed a formula to treat electrons as waves. The equation had only certain solutions, these quantized energy levels. Yes, this is part of the equation here, but very, we're not expecting you to calculate anything with it. But it does define probability, and if you notice anything about as math gets more higher up, you don't have as many numbers. You have lots more symbols and stuff in there. Okay? So he uses, and you're going to see a short video that has a lot of the math running through it, but that's not what's important. What's important is that he calculated these solutions, and then you could figure out the three-dimensional spaces as to where they're going to be located. And he was able to come up with the pictures of these three-dimensional spaces based off of his math calculations. So a high dot density means a greater probability of finding an electron in that particular space. And the solutions to the Schrodinger equation are known as wave functions. So the electrons have like wave functions. You know what functions are in math, and you can graph them and so forth. This idea here a little bit more complicated than just like algebra 2 math, but that's kind of the same concept here. Those wave functions. So the region in the space where we're going to likely find the electron 90% of the time is going to be that electron's orbital. This one is showing you an s orbital, and as you can see the tiny blue dots here, most of them, the higher density, is located in the center of that sphere. So the electron would reside in that particular three-dimensional space. Wave functions give the probability. So when we put an electron in an orbital or in an electron configuration, we're basically assigning it there where it's going to be 90% of the time, okay, around the nucleus. And they don't go around the nucleus in fixed orbits as Bohr suggested. The three-dimensional regions, and they're pretty interesting, you see them on your paper there, are known as orbitals, and those are those funny looking, they look a lot like balloons there, are going to be the three-dimensional spaces where electrons will reside in the electron cloud. So quantum theory of electrons, built upon numerous people here, but Schrodinger and Heisenberg really, formed it into this idea where electrons behave as waves and particles, and we're locating them 90% of the time probability of where they're likely to be. Okay? So here are some other pictures of the different orbitals. We're going to watch a short little video here that's going to kind of go through some of the talking points and maybe give you a better visual representation of what's going on here. So we're going to go ahead and do that real quick. But if you look here at our different orbitals, okay, the s orbital, there's only one orbital in an s sublevel. There are 3 orbitals in the p sublevel. They are the dumbbell-shaped ones. I'm sure you've all seen weights in the weight room, but that's where they're getting that idea to call it a dumbbell. The d's, which are in blue and purple up here, they end up being a lot more complicated. They look more like balloons to me, and of course the one in the middle is kind of like a donut-shaped one. And then the f orbitals down here in the green, there are 7 of them, as you can see. We even get the double donut one here. But these are three-dimensional spaces where we're going to be placing electrons in the electron cloud. Now, of course, we're not going to draw these. We're going to use boxes to represent the orbitals, and we're going to label the boxes with the S or the P or the D, and we're going to just use that kind of notation. That's called orbital diagram notation. But when you're putting an electron in a box that's labeled D2, we're going to be looking at maybe this orbital right here, the second d orbital, the second box of the d sublevel. You're placing an electron in that shape. Okay? So keep in mind we're going to be using boxes, but we're going to be placing them in the different orbitals, and they really are representative of what these shapes look like, where the electrons are going to spend their time. So let's go ahead and take a look at the video real quick, and we will go talk from there if we have time. It doesn't look like we're going to be able to make the video today, but we will look at it next class. So real quick before I let you go, the periodic table is set up and arranged with its atomic number, allows us to use it in an efficient way to track where the electrons are going to be. Now I had you label the blocks before, the S, the P, the D, and the F. And as you can see, with their rows, we can figure out which energy level they're in, which sublevel they're in and then which particular orbital they're in by using this diagram of the periodic table. And I'm going to show you how to do that next class, of how to come up with the electron configurations and the orbital diagrams using this as a tool. So you don't have to memorize it, you just have to be able to use the periodic table to help you figure it out.